Welcome everyone to the next video in discrete math series. If you are new to the channel, please subscribe the channel and watch the videos in sequential order so that you understand the concepts thoroughly, right? Without any further discussion, let us start the main topic of the day. So today we are going to talk about linear homogeneous recurrence relation, right? And rather we will talk about linear homogeneous recurrence relation with constant coefficient, right? In the previous two videos I talked about what is recurrence relation and how to formulate the recurrence relation, right? So in today's video we are going to talk about what is linear homogeneous recurrence relation, how to identify them and how to solve them, right? How to solve them means we are going to talk about a very general process that will help us to solve those recurrence relation which are linear and are with constant coefficients. Okay, so if I look at the definition here, a relation it's a recurrence relation rather is said to be a linear homogeneous recurrence relation with constant coefficient if it looks like this. Now let us delve into it. Let us talk about this expression to understand that what are those different terms that I am using basically mean. So first of all, why it is linear? Because if you look at all the terms here, an minus 1, an minus 2, an minus 3, an minus k, all these terms are just of degree 1, means an is of degree 1, and all the terms which we have used to write an are also of degree 1, right? So that is why it is linear. Second thing is why it is homogeneous. It is homogeneous because no term that occur are not the multiple of some of the terms like aj. Some terms like here, if you look at this, let us understand it like this. All the terms that is occurring in this expression are multiple of some n or some aj kind of term, right? So like it is an, like it is an minus 1, it is like an minus 2. So all these terms are occurring where they are in the recurrence relation are of multiple of some kind of aj term, right? Why it is of degree k? It is of degree k because the an has been written as the sum of its previous k terms, right? So you see I have written it an minus 1, an minus 2 and up to an minus k. So that is why it is of degree k. It is homogeneous, that I already explained. Why it is with constant coefficient? Because if you look at all the coefficient that is occurring here like c1, c2, c3 and up to ck, all are real terms and none of them are functions that depends on n. All are independent of n, all are constant. To understand it better, let us look at this first example and let us find out what kind of recurrence relation is this. So Pn is equal to 1.11 Pn minus 1. This is a linear homogeneous recurrence relation of degree 1. Why it is linear? Because Pn has power 1, Pn minus 1 has power 1. Why it is homogeneous? Because all the terms like Pn and Pn minus 1 that is occurring in this are the only term. There is no term which is not in the form of like some pj form, right? Not in the form of some pj. Why it is of degree 1? Because here you can see it is n minus 1. So the Pn has been written as just one of the previous terms. So that is why it is of degree 1. So the first one is, if I can write this first one is linear homogeneous recurrence relation. I am not writing the detail. Recurrence relation of degree 1. If you look at this expression, this is also linear because fn has been written as two of its previous term. The degrees of all the term like fn, fn minus 1, fn minus 2 are of 1. It is homogeneous because only fn kind of terms are occurring here or fj kind of terms are occurring here. and it is of degree 2 because fn has been written as 2 of its previous terms. So what I can do, I can write that this is a linear homogeneous recurrence relation of degree 2. What is this? This is also a and if I talk about this particular example, the coefficients are also constant, because what is the coefficient of fn1? What is the coefficient of fn minus 1? 1. What is the coefficient of fn minus 2? That is also 1. Now let us look at this. Is it homogeneous? Yes, it is homogeneous. Is it linear? Yes, it is linear. What is the degree of it? The degree of it is 5, because an is an minus 5. Now some of you might be thinking that here there is just one term, but what is happening here, I hope you noticed that I can think like an has been written as 0 an minus 1 plus 0 times an minus 2 plus 0 times an minus 3 plus 0 times an minus 4 plus 1 times an minus 5. So it has been written as 5 of its previous term, starting from an minus 1 to an minus 5, but the coefficients of all these terms are 0 except of an minus 5. So this is a linear, I repeat, this is a linear homogeneous recurrence relation of degree 5. What about this? This is a non-linear. This is not linear because if you look at this, the power of this is 2. The power of this term is 2, so this is non-linear. If I talk about this, this is linear, but it is not homogeneous. Why it is not homogeneous? Because this term 1 is occurring, which is not in the form of some hj. You see, that is what I talked about in the definition, that if I remove this one, suppose you forget about this one, then up to this, if I write just hn is equal to twice of hn minus 1, then it is linear. But because of this term 1, this is this is also linear, but because of this term 1, this is not homogeneous. So here I can also see it like hn minus 2 hn minus 1 is equal to 1. So if I am writing all the hi term in the left hand side, then we are getting a constant term which is not equal to 0 in the right hand side. So that is why this is not homogeneous. And if you look at the last example, in this last example, this is linear but not with constant coefficient, because here the coefficient is a multiple of n. I hope what I discussed here has made sense to you. In case if you still have doubt, let us go and check some more problem. So here we have a list of problem where we have to determine which of these are linear homogeneous recurrence relation with constant coefficient. Also find the degree of those that are, means those which are non-linear we don't have to talk about that, but those who are which are linear, for that I also have to find the degree. Now before I answer this question, I would expect you that you pause the video, write your own answer, and then match with the answer that I will be talking about. So if I look at the first example, you see that an has been written as 3 of its previous term, an minus 1, an minus 2, an minus 3. All the terms have AJ's type terms, like it is a1, it is an minus 1, it is an minus 2, means none of the term is occurring which is not some multiple of AJ type, if you allow me to use this, because every term is having AJ type thing. So this is homogeneous. For example, if I add plus 2 here, it will become non-homogeneous. I hope you got it. If I add plus 2, this expression will become what you call non-homogeneous. But right now it is homogeneous, it is linear. The coefficients are constant because you see 1, 3, 4 and 5 all are constant. And what is the degree of this? So degree of this is 3, because you can see we are going up to n minus 3. So what is the answer of the first one? It is linear, it is homogeneous, it is with constant coefficient, and what is its degree? Its degree is 3. Okay. If you talk about B, then B is not linear. Why B is not linear? rather B is they are asking this. When I'm saying not means they are asking determine which of these are linear homogeneous recurrence relation with constant coefficient. So certainly this is not with constant coefficient, because if you look at this, here we have 2n which is not the constant. So the answer for this is not a linear homogeneous recurrence relation with constant coefficient. If I talk about this is I mean, if I talk about the third one, what is third one? So you see this an minus 1 plus an minus 4. So is it homogeneous? Yes, it is homogeneous. Is it linear? It is linear. What is the degree of it? The degree of it is 4. What is the coefficient? All are constant. So this is, yes, this is a linear homogeneous recurrence relation with constant coefficient whose degree is equal to 4. If I talk about this is not homogeneous. No, this is not homogeneous. So this is certainly not linear homogeneous recurrence relation with constant coefficient. Why it is not so? Because it is not linear. Why it is not linear? Because of this term 2. If I remove this term 2 plus 2, then it will become linear. Is it linear? No, it is not linear, because the power of an minus 1 is 2. So it is not linear. So that is also no, it is not meeting the requirement. What about this? Yes, it is meeting the requirement. What is its degree? Its degree is equal to 2. Is it homogeneous? Yes, it is homogeneous. Is it with constant coefficient? Yes. So it is satisfying all the requirement. It is linear homogeneous with constant coefficient of degree 2. What about this? This is no, because it is non-homogeneous, because if you look at this an minus 1, we are getting n. So we have a term n which is not actually having the term aj, right? Because that I told you that it will be homogeneous only when the terms are just multiples of aj's, means some of the previous term. So for this also the answer is no. I hope you are getting this point. If you still have not got, put your comment that at what point you are getting confused, so that I can answer accordingly, right? Okay, so next we are going to talk about how to solve the homogeneous linear recurrence relation with constant coefficient. And to understand this, suppose we have a relation like this, right? I'm not going to use the term homogeneous linear recurrence relation every time, because it will be a slightly tedious job. So I will just use the recurrence relation, and in this context, whenever I am using the term recurrence relation, by that I mean the linear homogeneous recurrence relation with constant coefficient. Okay. Now those who have studied differential equation, they may see some similarity or some analogy between the argument that I am going to make. So suppose I call this equation number 1, and I am assuming that let an is equal to r to the power n is a solution of 1. When it will be a solution of 1? If means if and only if r to the power n satisfy this equation. An is equal to r to the power n should satisfy this equation. It means what? That if an is equal to r to the power n satisfy this equation, so this will become, in place of an I will write r to the power n. It will be c1 r to the power n minus 1. It will be c2 and an minus 2 will be r to the power n minus 2 plus c3 r to the power n minus 3, and so on up to ck r to the power n minus k, right? Now for this expression, what I can do, I divide both sides by r to the power n minus k. And here you need to be careful that when you divide it by r to the power n minus k, what will you get in the left hand side? You will get in the left hand side r to the power k. I hope you got it, because r to the power n by r to the power n minus k is basically r to the power n minus k. So this minus n and n cancel, you get r to the power k. What will you get here? You will get c1 r to the power k minus 1. You can check it, plus c2 r to the power k minus 2, and in the end what you are going to get, you are going to get ck, and r to the power n minus k will cancel the other term. So this I can write as rk minus c1 r to the power k minus 1 minus c2 r to the power k minus 2, and so on up to minus ck is equal to 0, and let me call this equation number 2. Now I told you that an is equal to r to the power n is a solution of this equation 1 if r is a solution of equation 2, right? So I repeat this argument, possibly you might have not got it properly, so let me repeat. I started this with the condition that I say an is equal to r to the power n is a solution of this equation number 1. Now if I am substituting this as a solution in this equation, I am getting the equation number 2. And what is this? This is a polynomial. This is a polynomial of degree k. Now if this is a polynomial of degree k, then it will have how many roots? It will have k roots. I hope you know that any polynomial of degree k will have k roots. So for each of the values that I get, suppose I get the values like r1, r2, r3 dot up to rk. So all these are the roots of this polynomial, right? Now what I'm saying that an is equal to r to the power n will be a solution if r1 is a root of this equation. So in that case we will get the solution like r1 to the power n. Similarly, if r2 is a root of this equation, in that case I will get the solution like r2 to the power n, and by combining all these we get the general solution, right? So when you combine all these solutions like r1 to the power n, r2 to the power n, and so on up to rk to the power n, you get the general solution. But before I talk about how to write the solution, I just want to highlight here that there are three possibilities whenever we are going to find the roots of the equation number 2, which is a polynomial of degree k. It will have k roots. Now the roots may be of different types. The roots may either be real or root or distinct root, real and distinct root. It may be some of the roots may be repeated roots, same roots, and it is also possible that the roots may be imaginary. So let us look at them one by one. So if I say that the roots are all distinct, and suppose they are r1, r2, r3 up to rk, then the solution of the recurrence relation is written as an is equal to c1 r1 to the power n, c2 r2 to the power n, c3 r3 to the power n, and ck rk to the power n. And I also believe that those who have studied linear differential equation, they can see some similarity between the two arguments. The second possibility is that when some of the roots are real but equal, right? So to illustrate that, I am starting with this possibility that suppose the two roots r1 and r2 are equal and they are equal to r. So in that case we write the solution as an is equal to c1 plus c2n r to the power n, right? Suppose we have three equal roots of the polynomial like r1, r2 and r3, and suppose they are equal to r. So corresponding to these three roots, the solution will be written as c1 plus c2n plus c3n square r to the power n. I hope you got it. Suppose we have four equal roots like r1 is equal to r2 is equal to r3 is equal to r4 is equal to r. In that case an will be what? An will be c1 plus c2n plus c3n square plus c4n cube and r to the power n. So these are the two of the possibility. I am also going to take problems on it. So don't worry that through the real example, we are going to discuss all this possibility. First, let me complete the theoretical aspect of it. So the next possibility is that what will happen when the roots are imaginary. So if we have imaginary roots, and you know from your earlier study that imaginary roots always occur in pair. So if alpha plus I beta is a root, then alpha minus I beta must also be a root. So in that case, if I write the solution, it will look like C1 alpha plus I beta to the power n plus C2 alpha minus I beta to the power n, right? But it is a standard practice that whenever we get imaginary root, we don't leave our solution like this. We try to get rid of the imaginary term. So how can we get rid of the imaginary term? That what we are going to do, I think you must have studied about writing the imaginary numbers in the polar form. So suppose you allow me to write alpha plus I beta is equal to rho cos theta plus I sin theta. If you do not know what is this, then put your comment in, put your doubts in the comment box. But since you have studied complex numbers in +2, I hope you might be aware that alpha plus I beta can be written in this form: rho cos theta plus I sin theta, and alpha minus I beta can be written as rho cos theta minus I sin theta. Usually we use R term here, but in this context I am using rho, right? And what is rho there? You remember this rho here is nothing but under root alpha square plus beta square, right? And what is this cos theta? Cos theta, which is nothing but I have written here that cos theta in this case is alpha by under root alpha square plus beta square, and sin theta is beta by under root alpha square plus beta square. So if I make this substitution, here in this solution, the an will become what? The an will become C1, and for this I have to take the power n. So rho to the power n will become this, and here if I take the power of n this, possibly you might also be aware that cos theta plus I sin theta to the power n using de Moivre's theorem can be written as cos n theta plus I sin n theta. So this will become what? This will become cos n theta plus iota sin n theta, right? And the other term will be C2 rho to the power n, and it will become cos n theta minus iota sin n theta. So now what we do, we combine the terms. So we take rho to the power n common, and we have cos n theta here, we have cos n theta here. So the coefficients like C1 plus C2 will come common, and we will write cos n theta. And then rho to the power n I already have taken common. So if I take C1i here, the first coefficient I times C1, and the second coefficient for sin theta will be minus I times C2, and I can write this as sin n theta. So in the end, when we have to represent the solution, we represent the solution like what? Rho to the power n, rho to the power n. And for C1 plus C2, I use a capital C1, means another constant C1 cos n theta. And for IC1 minus IC2, I use the capital C2 sin n theta, right? So this is how we write our general solution, that an is equal to rho to the power n C1 cos n theta plus C2 sin n theta, where what is rho? Rho is under root alpha square plus beta square. What is cos theta? Cos theta is alpha by under root alpha square plus beta square. And what is sin theta? That is beta by under root alpha square plus beta square. And this capital C1 that we have written here is nothing but what is this? C1 a small c1 plus a small c2, and capital C2 is I times C1 minus C2. Oh, sorry. So the point I just completed, that whenever we get imaginary pair of roots alpha plus I beta and alpha minus I beta, we don't write our solution like this. We write our solution like rho to the power n C1 cos n theta plus C2 sin n theta, And then we also specify that what is the rho and what is cos theta and what is sin theta. So I will explain these things through examples. So I am going to take some different kind of examples. So keep watching. We are going to take examples further. Okay, so let us solve this problem to understand the process that we have just explained. So to solve this linear recurrence relation with constant coefficient which is homogeneous, the first thing that we have to do, that we have to write the characteristic equation. And if you have understood the process that I discussed while discussing that what is the steps involved in writing the characteristic equation, you can write the characteristic equation directly. So what will be the characteristic equation? We have an, so we can write r square is equal to r plus 2. Now I hope you got it. If you didn't get, let me explain it again. So what I told you earlier, that to write the characteristic equation, we consider that an is equal to r to the power n is the solution. If r to the power n is the solution, this expression will become what? This will become r to the power n is equal to r to the power n minus 1 plus 2r to the power n minus 2. Now you can divide both sides by r to the power n minus 2, right? So if you divide rn by r to the power n minus 2, it will become r square. If you divide r to the power n minus 1 by r to the power n minus 2, it will become r. And if you divide 2r to the power n minus 2 by r to the power n minus 2, this term will cancel and you will get 2. So the characteristic equation will be like r square is equal to r plus 2. So now I have got the characteristic equation r square minus r minus 2 is equal to 0. And we solve it to get the roots. So r square minus 2r plus r minus 2 is equal to 0, which will give me r common r minus 2 plus 1 common r minus 2 is equal to 0, and that will give me the root r is equal to 2 and minus 1. So the solution that I will write is, and now these roots are both real roots and distinct root. So the solution that I will write is c1, real root means 2 to the power n, plus c2 and the second root, that is minus 1 to the power n. Let us call this equation number. Now the next thing that we look at is that this solution, if I call it a general solution, has two arbitrary constants c1 and c2, and in the problem they also have provided us with two initial conditions a0 and a1. So using these two initial conditions, we will be able to find these two arbitrary constant. I hope you are aware about this thing, that to get n arbitrary constant we require n initial condition. So if I have a0 is equal to 2, means what I can write, I will replace n is equal to 0. So 2 to the power 0, so it will become c1 2 to the power 0 plus c2 minus 1 to the power 0, and that an is given to be 2, so it is equal to 2. So this will give me, this is 1, this is 1, so it will give me c1 plus c2 is equal to 2. And if I take a1 is equal to 7, this will give me what? c1 2 to the power 1 plus c2 minus 1 to the power 1 is equal to 7. So I get 2c1 minus c2 is equal to 7. Now we have these two equations, we have to solve them. So it is very obvious that we just add, we get 3c1 is equal to 9. So that will give me c1 is equal to 3. And once we have got c1 is equal to 3, using this equation I can get c2 is equal to, means I am saying this 2 minus c1, so that is 2 minus 3 is equal to minus 1. So we have got two arbitrary constants. So what is the solution now? Solution is c1, an is equal to c1, that is 3 2 to the power n, minus c2, that is minus 1 minus 1 to the power n. So this is the solution of this recurrence relation. I hope you have got the point. The important thing while solving the problem is to be able to write the characteristic equation correctly. So we are going to do some more problem, and through that we will be able to understand the process even better. So let us move to the next problem. Now look at this problem. So the problem is an is equal to 6a(n minus 1) minus 9a(n minus 2). So here also, if I have to write the characteristic equation, I hope by now you are comfortable. I am writing it directly. It is of degree 2. This is a recurrence relation of degree 2. So it will be a 2-degree polynomial. So an I will write r square. It will be 6r minus 9. So basically you think it like this, that you have n minus 2, that is the lowest degree term. So basically you are replacing this by a constant, and other terms you are multiplying it by increasing the powers of r. So you can consider it that here you have r to the power 0. It is n minus 1, 1 more than this, so it is r, and it is an 2 more than n minus 2, so it is r square, right? Still, if you have not understood, you can go by the process that I explained, that you can consider replacing an by r to the power n, an minus 1 by r to the power n minus 1, and an minus 2 by r to the power n minus 2, and dividing both sides by r to the power n minus 2, you will get r square is equal to 6r minus 9, right? So if I solve this, I will get r square minus 6r plus 9 is equal to 0. And this is a very standard looking expression, nothing but r minus 3 whole square is equal to 0. So we get r is equal to 3 and 3. So now this problem is different from the previous problem in sense that here we have two repeated roots, means both the roots are not distinct but rather the same roots. So the second type that we have seen, in this case the solutions would be written as c1 plus c2n and 3 to the power n, right? But here also they have provided us with two general or two conditions which we call initial condition. So we can use these initial conditions to find the value of c1 and c2. So let us find the value of c1 and c2 and see what we are getting. So let me call this equation number 1. So first condition is a0 is equal to 1. So if a0 is equal to 1 means I have to put n is equal to 0. So I will take c1 and n is equal to 0. So c2 into 0 and 3 to the power 0, and that is equal to a0 is equal to 1. So basically what we are getting from here, c1, c2 into 0 will be 0 and 3 to the power 0 will be 1. So I am getting c1 is equal to 1. We don't have to put extra effort because this becomes 0 and this becomes 1. So basically we are getting c1 plus 0 into 1, so that is c1. And if we have a1 is equal to 6, so this will give me what? This will give me c1 and c2 into 1, right? And 3 to the power 1 is equal to 6. So this gives me c1 plus c2 and 3 is equal to 6. Now if I solve it further, I can continue writing here. So I will get c1 is equal to also 1, right? So we can look at it like this. We can consider writing c1 plus c2 is equal to 6 by 3, that is equal to 2. And from here I will get c2 is equal to 2 minus c1, that is equal to 2 minus 1 is equal to 1. So c1 is also 1, c2 is also 1. So what is an? An is 1, c1 is 1 and c2 is 1. So 1 into n is n, so 1 plus n and 3 to the power n, which if you wish to write can also write 3 to the power n plus n into 3 to the power n. So this is how we get the solution for the recurrence relation in case when the roots are repeated, right? We will also take problems where the roots are imaginary. Okay, fine. So let's move to the next problem. Now in this problem I have not been provided with any initial condition, so I just have to solve it till the getting the general solution. So I don't know if you are comfortable writing the characteristic equation, and I hope I have used the term characteristic equation because in differential equation we use the term auxiliary equation. So what will be the characteristic equation here? So I am writing it directly, and if you still not comfortable, I will explain you through that process. So n minus 2, so I am considering that I have to write a polynomial of degree 2. So the difference here an and n minus 2, so I will write r square is equal to r minus 1. So this will be like r square minus r plus 1 is equal to 0. I hope you can see it directly. If you still have not been able to see, then consider an as r to the power n, an minus 1 as r to the power n minus 1, and this is r to the power n minus 2. And now divide both sides by r to the power n minus 2. So you will get r square is equal to r minus 1. So you get r square minus r plus 1 is equal to 0. Right. Can we think of it in a better way to be able to write this? So I think what is the better way to explain? A n minus 2, so lowest term with like lowest n minus 2 term is there. So for that we are replacing it by a constant, and then the next n minus 2, what is the next n minus 1? So that we are replacing by r. What is the next term? N. So that we are replacing by r square. Let's take one example here where suppose we have a recurrence relation like an is equal to an minus 1 plus n minus 1 plus 6 an minus 2 minus an minus 3. So if I have to write the characteristic equation, we have n minus 3, so that I am replacing by the constant term. So that will be like minus 1. Right, this minus whatever constant that will be there, so it is minus 1, so minus 1. Now the next of n minus 3 is n minus 2, so that I am replacing by r. So this term will be plus 6r. Then this will be next n minus 2, so this will be r square, so I will write r square. And this is the next term, so I will write it r cube. So this is how I think you should be able to write the characteristic equation. So now let us come to this problem. So if I look at this expression, I can clearly see that here the roots are imaginary. So using the formula, I can write minus b, so minus 1, so 1, and plus minus b square. So b square here is minus 1 square minus 4 into 1 into 1, and by 2a, that is 1. So we are getting the roots 1 plus minus, and 1 minus 4 is equal to under root 3 iota, and by 2. So we have got an imaginary pair of root, like that is 1 by 2 plus minus root 3 by 2i. And in this case, if you remember, I have the general solution that we write as rho to the power n c1 cos n theta plus c2 sin n theta, right? This is how we have written the general solution. And we also have specified that if I am calling this as alpha plus minus I beta, then rho there is equal to under root alpha square plus beta square. So in my case, what will be rho here? Under root alpha. So what is alpha here? 1 by 2 square. So it is 1 by 4. And beta is under root 3 by 2. So if I square it, I will get 3 by 4. So I get 4 by 4. So that is equal to 1. And what is cos theta? Cos theta is alpha. So what is alpha here? 1 by 2, and by under root alpha square plus beta square that we have got is 1. So cos theta is equal to 1 by 2. And similarly, what is sin theta here? Sin theta is under root 3 by 2 divided by under root 1. So that is same thing. Okay. So what is the solution in this case? The solution in this case is an is equal to rho is 1, so 1 to the power n. Let us write it, but I think it is not needed because 1 to the power n is 1. And then we write c1 cos n theta plus c2 sin n theta. But theta is something that we have introduced from our side. So let me finally write it. c1 cos n theta plus c2 sin n theta, where let us, because 1 to the power n is just 1, and where you specify that cos theta is equal to 1 by 2 and sin theta is equal to under root 3 by 2. I hope you remember this, that when I discussed earlier, we write cos theta is equal to alpha by under root alpha square plus beta square. Because under root alpha square plus beta square is 1 here, so this will just be alpha, and sin theta we told was beta by under root alpha square plus beta square. So here it is just beta, which is under root 3 by 2. So this is how you write the general solution in case of imaginary root. So we have taken 3 problems where we have discussed 3 cases. One where the roots were real and distinct, other where roots were same, and then the third problem where the roots are imaginary. So I hope you have got it. Do some practice, and in case of doubt, let me know. So this is all for this video. In the next video I will try to solve some more problem. If you are new to the channel, please do subscribe and share with your friends also. Thank you.